Good evening, everyone. Welcome to today's guest lecture. So today we have Dr. Sharma. Pranay is an associate professor at IIT Bombay in the Center of Information Intelligence and Data Science. Prior to joining 6 months IIT Bombay, he was a research scientist in the Department of Electrical and Computer Engineering at Carnegie University. In August 2021, he finished his PhD in Electrical Engineering and Computer Science at Syracuse University. Before that, he finished his BTech and Tech Geology program in Electrical Engineering from IIT Bombay. His interests include federated and collaborative learning, stochastic optimization, deep learning theories, reinforcement learning, and differential privacy. So, what is it?
Can you hear me, everyone? Can you see this? Those on the right, can you see this? Those on the left, can you see this? And can everyone see this? Okay, so hopefully these are the three mathematical things I'll need in today's lecture. So thanks for the introduction. Thanks for the invite. I'm an assistant professor, not an associate professor, you said. So I don't remember, but yeah, just to get the record straight. I'm an assistant professor joined here in Feb. I'm teaching a course of my own, which is federated learning, distributed learning, decentralized learning, optimization. So my course has 10 students, and there are 2 or 3 others who come to the class in every class. So I'm used to teaching 12 to 13 people in a much smaller room. So yeah, you will have to remind me if you have any questions. I might not look up in this entire field of view. Okay, so as the kind introduction said, I work in federated learning stochastic optimization. So at least on paper, I'm not suited to give a lecture in this course because I don't work in NLP. But I work in a number of things which will have bearing on NLP in a certain applications if you choose to work in them. And because I work in theory, so I work in general enough problems which can be specialized to a lot of domains. Okay, so I don't work on vision specific or robotics or natural language based applications, but what I do can be generalized to a number of settings. So differential privacy is something I work in, and privacy has applications in a number of things. So because you are in an NLP course, you know about ChatGPT, and there is a lot of conversation about the privacy of the data on which ChatGPT was trained on. Okay, so in today's lecture, I will give a brief overview of some of my work. So I'll explain the first word of the title, what federated means. How many of you know what federated learning is? Okay, one. Okay, good. So I'll give an introduction of federated learning for the initial, I hope, 1/3 of the lecture. And then I'll go to something more specific, which was my work. It got published in AI Stats this year. And I'll try to motivate that this has applications in a lot of domains you might be interested in an NLP course. Okay, so let's get started. So this work was done while I was at CLU. So the first picture is Barish. He is a PhD student. He was a PhD student in the group I was in. And the other 2 people are Professor Gauri Joshi. So Gauri is an alum of IIT Bombay from a few years back. And she's now a faculty member there. She was also my postdoc supervisor. And Professor Kari Jo Wong. So it doesn't need any introduction that we are in the age of big data. So big data was the buzzword in the 2010s. Now it has been overshadowed by AI, but big data was the big buzzword when I was even while I was doing my PhD, which was like a few years ago. And the thing with big data applications is that whichever application you look at, whether it is something in your smartphones, or is it healthcare, or is it e-commerce websites, it needs a lot of data, right? And the data is often naturally distributed. It comes from a number of sources. It might come from your devices, like your laptops, smartphones, tablets, or it might come from your health monitoring devices, or it might come from devices in our homes, such as televisions, cameras, and so on. And this data is then used to train machine learning models to do a number of things. Okay. So let's look at a few example applications. This is an example of an image recognition, image classification application, where let's say we have camera feeds from a number of devices all over the city. So we are supposed to have smart cities. A few cities in the world already are. But suppose we have camera feeds from a number of devices all over a city, and we are monitoring the traffic patterns. These can come from traffic cameras, but they can also come from individual handheld devices, right? And we want to somehow do some kind of task, for example, predicting traffic patterns or classifying road signs, where there is a speed limit sign, where there is a traffic light, and so on, using this data field coming from a number of devices. Another application is which people in this course would be probably more interested in. This is the predictive typing application. So this is a next word prediction model, where as you type on your phone, it gives you suggestions for what you might intend to type next, right? So you might remember the first time you installed WhatsApp. The suggestions were quite generic and came from basic English grammar. But we might use WhatsApp typing in a number of ways. For example, if you speak Hindi or Marathi, you might be typing in the English language, but what you are writing is actually Hindi, right? And over time, you would have noticed that it learns the patterns of your language and would suggest words accordingly, right? So a number of users all over the world are typing, and you are supposed to learn something from all that data while still maintain the personalization of your own language. Okay. Something even more ambitious is autonomous driving, which is at least for the past 20 years, it has always been possible in the next 2 or 3 years. So in autonomous driving, if and when it gets realized, so you have a bunch of devices which can monitor their surroundings and do make some kind of decisions based on that surroundings. This can potentially lead to much smoother traffic, and it understandably also has a lot of security and safety concerns. So in all these applications, what is common is that you have a server at the top, which is sort of coordinating the operation in that application. And then you have a bunch of devices. So these can be the cameras in the first application. These can be phones in the second application, and these can be individual vehicles in the third application. I've shown them generically as a phone. So the server is supposed to coordinate the operation across these multiple devices. The devices are not going to talk to each other in this talk, but they talk to the server talks back to them. So the communication in general, it can be either device to server or it can be between devices themselves. However, in this talk, we will only focus on device to server and server to device communication. Okay. So what are the challenges to learning in such a setting? Any suggestions? Any ideas? What would be some challenges? Yes. Sorry. Privacy. You don't want to leak individual user data. Any other? Storage is an issue. So this traffic feed, suppose we somehow took care of privacy, even then you don't want to send an entire privatized feed of a single device to some central location. Storage is an issue. What else? Communication is a challenge. How do we communicate so much data across from the devices to the server and back? How do we do that? Anything else? Sorry? Latency comes under communication, but yeah, sure. Latency is a big challenge. You need to synchronize these updates across different sources. These are very good suggestions. and you are touching about several aspects of federated learning, some of which we will talk about. Anything else? Are your smartphones always on? Usually you would see that when you plug your phone into charging at night, it's only then that apps get updated. It's only then that your phone is available for some kind of operation with the server, some server, right? So device availability is a challenge. Your device is not always available. You might not always point your camera towards the traffic scene, right? So based on your suggestions, privacy of the user data should not be compromised because we care about privacy. Communication is a challenge. So this is like a weighted map which shows 5G connectivity worldwide about 3 years ago. Okay, so situation would only have improved in the past 3 years, but you can still imagine that there are parts of the world where communication connectivity is not as good. And even when bandwidth improves, the new applications require more and more bandwidth, right? So back in the day, when I saw YouTube for the first time, most videos had 480p as the best resolution. Now, what is the best resolution? I think there's 4400 in some videos, right? So the requirement also improves if the bandwidth improves. So, and communication is often expensive. And finally, the availability of devices is not guaranteed at all times. The devices are only available when they are idle, plugged into charging, and on a Wi-Fi net. Right? So this figure shows a cartoonish image of how devices become available. So the dark regions are where there is night. So usually you plug your phones into charging at night, and you're at home, so you have a Wi-Fi network, hopefully. So that's when these devices are available. And as time progresses during the day, different set of devices become available. Right? So you want to do distributed learning, you have data coming from distributed set of devices. You want to care about privacy, so you cannot just send raw data. You want to care about communication constraints, and you want to care about partial availability of devices. So all these constraints led to a paradigm called federated learning. The first paper which proposed it appeared in AI Stats 2017. So about 8.5 years ago, or it must have been submitted around this time, so about 9 years ago. And I checked a few days back, it already has 29,000 citations. So it's a very extensively studied field. Okay. And we'll do a whirlwind tour of it today. So let's look at a toy example of how a typical federated learning algorithm proceeds. Okay. So suppose you have a bunch of devices. You have a server at the top, and all these devices are colored in different colors. Why would they be colored in different colors? Other than aesthetic value? What would the different colors symbolize here? Any suggestions? Okay. Users, different kinds of users, and sorry, right, locations. So there is a lot of heterogeneity across these users. Okay. So different colors of users indicate different kinds of data they might have. They indicate different locations. They indicate different kinds of devices. Someone owns an iPhone, someone owns a very cheap smartphone. Okay, but they are running many of the same applications. So they'll have different processing powers. Okay, so suppose going back to our predictive typing application. Suppose this is the application we are concerned with. We have a server at the top coordinating this operation. But as different colors of these devices indicate, there is a lot of variation even in the data of these devices. For example, for some users, it might be a simple piece of prose you would read in a normal English text, right? So in a small town, greengrocer and operate the store located about each other, etc. Or someone with some inclination towards poetry might have this as the text they are interested in. Where is this from? The text in the middle. Where is this from? Where the mind is without fear. Has anyone heard of that? Okay, it's a very famous one. Maybe it was famous when I was growing up. So it's a poem called Where the Mind is Without Fear by Rabindranath. So someone with a lot of inclination towards poetry might have this text. Someone closer to your age might have this kind of text. Okay. I had to actually Google these. I didn't know the meaning of several of these. Okay. So the kind of data you have, the kind of data you are typing in your phone varies across users, right? And we are supposed to learn collaboratively across these multiple users with all this heterogeneity. Okay. So let's see how a typical algorithm works. Again, so there is data heterogeneity. Also, because there are different kinds of phones, different manufacturers, different computation power, different memory. So you also have a lot of different kind of networks they are working on. So you also have a lot of heterogeneity across these devices. And we are supposed to learn and given all this variation and all these constraints. So how a typical algorithm works is it proceeds in what we call rounds. Okay. So suppose a specific round begins. You pick a certain set of users from the set that is available to you. For example, in this round, let's say these three devices become available to you. And this is like a very small fraction. Usually this fraction is 1% or even less than that. So if millions of devices are running an application, at any time you might have a few thousand or a few hundred devices to work with. So in the beginning, to these available devices, the server sends its current global model. So whatever the WhatsApp model is right now, this when your app gets updated. So in the beginning, you have this basic model. Starting from this basic model, right? So there is communication efficiency involved here. You need to respect the communication constraint. If you have a model worth several megabytes, you need to somehow compress it and make sure it satisfies all the constraints you have. Then, starting from this common global model, each client, each user would update this model using its own data. So someone with poetic data, poetic text would update model accordingly. Someone with slangs will update it accordingly. And this process repeats a certain number of times. And at the end, different clients come up with a different model. So they all started with this black model. And now everyone has a different kind of model. Or the same kind of model, but with very different looking weights. Okay. And now you need to, in this process, you need to remember that these are low power devices, like your smartphone, as opposed to what Apple or Samsung would like to have you believe, doesn't have infinite compute. So you have to respect these constraints of the device when they are running this local training. Okay. So usually, does everyone know what first order methods are? Gradient based methods, gradient descent. Okay, nice. So basically gradient descent kind of methods are what we use. Once the clients or users are done, they would send back their model back to the server. So when you see this upward arrow blinking on your phone, when an app is getting updated, this is what is happening. Okay. Again, you need to satisfy the network constraints. And then the server would take all these local models that you send and would somehow aggregate them to get a new model. So starting from these number of models, which all these three clients had sent, it would come up with a new model. Okay. So this concludes one round of federated learning. Round T ends. So what did we do? In the beginning, a small set of devices became available. The server sent its current model to those clients. The clients did some local training using their own local data. And then once they were done, they sent back these updated models back to the clients. And the client, they sent back these updated models back to the server. The server somehow aggregated them and came up with a new model. Okay. This concludes one round. In the next round, a new set of clients might become available. Okay. And then the process continues. Any questions so far? These can be the, yeah, so again, number of variations of it, that's why I said 28,000 citations. So in the beginning, all these local models were the same architecture as the initial model, but there are subsequent innovations in which you can have much smaller models at the time. So
yeah, when in the next round we have new set of vessels, they maybe the case that certain users are always on time or always active. They don't balance out the overtaking of the question.
right. So in practice, there are several ways to deal with this. One way is you can issue some kind of timeout. That once you have participated in one round, you cannot appear for the next 100 rounds. So that is one way. It's also not in the user's best interest to always be available because you will lose more privacy. So, like, how privacy is ensured is very quickly. You want to minimize the exposure of your data to the server, and the more you participate, the more privacy you will lose. So, from the perspective of privacy, it's in the user's interest to not participate very frequently. Okay. Any other questions? Yes.
So would there be a problem?
Won't there be a problem of forgetting? Great question. So won't there be a problem of forgetting in this? There are some ways to, again, so I'm more interested in the theoretical aspects of these problems. So this problem of catastrophic forgetting, it's understood very little from a theoretical perspective. There are heuristics people use to ensure that that doesn't happen. Suppose you have, you can, for example, cluster your clients into different kind of groups. That these groups look similar, these groups look similar, clients in this group look similar. And then you can make sure that clients from each group participate frequently enough so that this doesn't happen. But the fundamental understanding of why catastrophic forgetting happens, how to avoid it, still lacking. Any other questions? That's a great question. Okay, so let's continue. So this was, and there are this algorithm proceeds in rounds. You get certain number of rounds in total. This can even be a continuing process. Okay. So this was a whirlwind tour of very abridged edition of what federated learning looks like. I've missed a lot of things here, so come talk to me if you want to know more. But this was the introduction to federated learning. Now let's discuss what is the specific problem we are solving here. So let's discuss with start with a few applications again. So again, all of you know about chatbots, and you have used several of them. So in all these chatbots, when you interact with them, they are not just trying to optimize one objective. When we start solving machine learning problems, for example, when you are trying to generate text or when you are trying to build an image classification model, usually the task is much simpler with a single objective. You might want to increase the classification accuracy or minimize some error, right? But usually these large scale production scale systems, there are a lot of objectives which you are simultaneously trying to balance. For example, you of course care about the accuracy and relevance. ChatGPT should tell you what you ask it, not some random facts, right? But it also cares about engagement. That's why it tries to act friendly. Whenever you ask it a question, it comes up with some phrase like "great question," even though you don't really care about it. Also, it needs to be polite, it needs to be safe, it needs to avoid abusive language. And you would also, maybe some people would prefer some kind of personalization. I hate that kind of personalization. I hate it when ChatGPT says great question. I don't care about your opinion, but some people might appreciate that. So, and in all these multiple objectives, you have multiple trade-offs, right? If you care about privacy, in a few cases, personalization might hurt your privacy. if you care about accuracy, personalization might hurt your accuracy, right? So all these different objectives come up with some kind of trade-off when you prioritize one over the other. Let's look at another example. So recommender system, again, something all of you must have interacted with in Amazon or Flipkart or YouTube or Instagram. So here you have multiple users interacting with these systems. So of course, data privacy is an issue. You don't want everyone to know what you're watching on YouTube, right? You don't want everyone to know all that you browsed on Flipkart, right? But even from the systems perspective, there are multiple objectives. They care about things being relevant to you, right? In monsoon, you don't want Amazon to suggest snow boots to you, right? They also care about diversity, right? So if you once browsed for earphones, it doesn't mean it should just suggest earphones to you. It should suggest other electronics products as well. You care about novelty. Once in a while, you would like to see some very new kind of product. You might not like it always, but sometimes you might end up buying something you didn't intend to buy. Okay. And then there is contextual relevance. The example that I gave, it's your context that you are living in Mumbai and this is monsoon season, hopefully towards the end, right? So it is not relevant to you to suggest no boots. Again, with all these multiple objectives, you come across multiple trade-offs. If you suggest diverse set of items, not all of them might be relevant to you. But what does the system want to prioritize? Does it prioritize diversity over relevance or the other way? Right? Let's look at one more example, which is actually a serious application in my opinion. So this is personalized medicine, and a lot of people believe that in the coming decades, this would become a reality. So again, you have multiple patients, and there is diversity of data across these patients. What do I mean by that is, so some of you who would go to US, you will see that initially, as soon as you reach there, they will do your chest X-ray if you go there as a student, and with a high probability, they would diagnose you with TB, right? So for Indian student, it's a big shock because from the background we come from, we are fortunate enough to not have TB in India, right? But TB is an eradicated disease, almost an eradicated disease in the US, while it's not in India. So their threshold for TB is so low that most of the students end up showing as having latent TB on their X-rays, right? So there is diversity across patients, while very few students who are like born and raised in US end up with those results. So there is diversity across patients. Of course, you care about confidentiality of the data because what disease you might have is a private information. But even from the system's perspective, again, there are multiple objectives. So of course, you want to be accurate in your diagnosis, but you cannot throw all the tests in the world. So you can test someone for 100 things and then come up with a very accurate prediction of what you might have, but that's not cost effective. So you care about cost effectiveness as well. You care about equity in access. So cost effectiveness is also linked to how equitable healthcare or personalized medicine is to everyone, right? So you care about these things as well. And again, with the example I gave between diagnostic precision and cost effectiveness, there are trade-offs in them. So how do we navigate these trade-offs, right? So the common theme across all these three examples, whether we look at chatbots or we look at recommender systems or we look at personalized medicine, the common theme is that we have data from multiple users, multiple clients, multiple patients, and we want to learn a model which simultaneously does multiple things or simultaneously does well on multiple things, right? So that's the problem we want to solve. Any questions so far? Okay. So getting a little mathematical, I would skip a lot of mathematical details, but the basic problem formulation I think is important. So I'm writing it here, and on that side you can look at it again and again. So as you must have seen in this course and a number of other courses, we often try to pose the problem we are trying to solve as an optimization problem mathematically, and then see how we solve this mathematical problem. And then we go away from the mathematical solution and try to make it work in practice. So that's what we will do as well. Suppose we have m objectives. So m is the total number of objectives. And we are trying to minimize a vector of all these losses. So we have m losses, and we are trying to minimize all of them simultaneously. Each of these n losses, let's take the kth loss. Each of these losses is averaged across multiple users. Okay. So we have n users and we have m objectives, and each of the loss is averaged across all the users. Okay. Is that fine? So in each loss, the subscript will denote the specific objective. So K is for the objective, and the superscript will denote the specific client or the specific user. So I is for the client. So L sub K sub I is the loss corresponding to the kth objective at the ith client. Okay. So this is the problem we are trying to solve. This is different from what you are used to, because usually you are used to solving this problem. Minimize a function f with respect to x, right? This is usually a scalar function, but now you're trying to minimize a vector. What does that even mean? What do you mean by minimizing a vector? Right? So let's see. So again, this is the schematic. The server wants to minimize this vector of losses, and each entry of this vector is distributed across multiple users. So at each user, you would note that there is a vector of losses. The subscript denotes the specific objective. So there are 1 to n objectives, and the superscript denotes the specific user. So the superscript is common at each user. Okay. And in this talk, we'll talk about an algorithm called FED-CMO. It's Federated Communication Efficient Multi-Objective Optimization. Multi-objective optimization because we are solving multiple objectives, right? Communication efficient, we'll get to that in a minute. And federated because the data is distributed across multiple devices. Okay. So we'll see that the communication cost, which we discussed very briefly, that is an issue. If you have a very large model, if you have a model which is, let's say, a few megabytes or a few hundreds of megabytes, then you don't want a separate model for each objective, right? In the examples I talked about, for example, recommender systems, I listed 5 objectives. Usually in these platforms, they have hundreds of objectives, right? So if you have each model worth a few hundred megabytes, you don't want to communicate tens of GBs of data every time you update a model for each client. They might not even have that much memory, right? So this algorithm, yes. Right. So we would try not to do that. Okay. So just to give an example, suppose here you plot f1 of x, and here you plot f2 of x. As you change x, you get a separate point on this. And suppose you get this surface. So how do you compare this point with this point? Here, f2 is smaller, but f1 is larger. And here, f1 is smaller, but f2 is larger. You can't really compare these points unless you make a judgment choice that I care about one more than the other, right? So that's essentially the challenge in doing multi-objective optimization, that you don't get clear-cut answers like you do with simple scalar minimization. Okay, but that's also what makes it interesting and opens up a lot of open questions.
Previous slide, the number of objectives and the user was same.
So there were n users and m objectives. Okay. Any other questions? Okay. Good question. And we show convergence to something called a Pareto stationary point. So everyone knows what a stationary point is. What's a stationary point? A little more mathematically, where the gradient is zero. So if you are solving this problem, if you want to minimize a function f of x, any point where the gradient is zero is the stationary point of this function. But this definition holds for scalar objectives. When you go to vector objectives, you have to generalize it. And this generalization is called Pareto stationarity. Okay. So this curve is called a Pareto front. Okay. And yeah, we showed some improvement compared to state of the art. And we had some improved empirical performance. But I think the main contribution of the work is that your communication cost does not scale up with the number of objectives. And then you can translate it to your favorite application. You might want to fine tune some very large language model, or you might want to train a computer vision model to do something, to train a model which does multiple objectives and so on. But our algorithm gives you guarantees which are domain agnostic. Okay. So this is the outline of what I'll do going forward. I'll first give a brief overview of multi-objective optimization. I think that is necessary because you are used to this, and I want to take you to this. So to bridge the gap, I'll talk briefly about multi-objective optimization. I'll talk about something which looks very similar to gradient descent, but ends up solving this problem. So this is called the MGDF, and then we'll go along. Okay, so first, let me ask this question. So why are we even solving this multi-objective problem? Like, okay, sure, I'm motivated why we care about multiple objectives, but why don't we solve this problem? Where we just take a linear combination of all the objectives and we get a scalar function, which is what we know very well how to do. So why are we solving this vector minimization problem, which looks significantly more complicated? Why should we do that? Why not minimize a scalar objective, which is just a linear combination of all the different objectives? What could be the reason for not doing that? Any suggestions, guesses? Okay, so yeah.
Tools like you mentioned accuracy and personalization. Are these tools can categorize these two as objectives?
Sure. Like some metric you can come. So accuracy is similar. You can minimize some loss. That would lead to more accuracy. So then you can come up with a metric for personalization. VR.
If we want to do this, we can suggest if some result was more personalized.
Yes. Yes. So what's the problem with doing that? Yes. Right. So it assumes that I have made some choice about the weights, these alpha k's. How do I come up with that? Okay. So in a lot of problems, it's not clear what do I actually want? What do I want to prioritize? Maybe I want to explore a lot of options and then choose what should I do. So maybe I shouldn't settle on a weight in the beginning. Also, when you do that, so this is an empirical observation, that when you do this type of a thing, where you minimize the scalarized loss, then you end up doing very badly on some of the tasks. Whatever the choice of weights you come up with, suppose you are doing very badly, let's say on 5 out of 50 classes, then you would want to give higher weight to those 5 tasks, but that would necessarily lead to the other tasks doing badly. So empirically, it's very difficult to get a good balance in these cases. And my favorite explanation that you can theoretically show that if you solve this linear problem, this linearized loss problem, and you look at all possible weights, all possible choices of alpha, even then, the set of solutions that you get. So you will get one solution for each value of this alpha vector, right? The set of solutions you get by looking at all possible values of alpha is much smaller than the set of solutions you can get by solving the original problem. Okay, so you are leaving a lot on the table by doing this simplification. It's simpler to solve, but you are leaving a lot on the table. Okay, so there was a NeurIPS paper in 2023 which actually showed that this kind of linearization leads to a much smaller solution set, and you shouldn't do that. Okay. Any questions so far? Okay. So finally, I want to really convince you that what I'm saying actually also has some effect in practice. Yes, yes, yes. Yes. Because so in this problem, you are essentially so let's assume this is your loss vector L1 to Ln, right? You see this? Okay, and you are taking these weights and you have taken a linear combination of them, and that's what is happening here, right? You have significantly reduced your degrees of freedom, right? It is possible that if you had not restricted yourself to just a linear combination of these weights. So doing a linear combination of these losses, it's a very specific thing. You could have done something else also, right? Why would you limit yourself to just linear combination? You could do something non-linear combination. For example, f1 plus mod of x, mod of x, right? So the set of possibilities with just linear combinations is much smaller. Okay. Okay, so like just to finally convince you once and for all, at least with one example, that this actually affects things in practice. So let's look at an example. So this is a very famous paper from NeurIPS 2018. They did an experiment. They artificially constructed a data set from MNIST dataset. Everyone knows what MNIST is? Okay. So what they did was they artificially created images which had one digit in the top left and one digit in the bottom right. Okay. And for every image, there were two objectives. One was to classify the top left image accurately, the top left digit accurately, and the other was to classify the bottom right digit accurately. These were two separate tasks, two separate objectives for every image. Okay, so you get your two objectives. And then they tried out a number of methods. So these stars that you see, these stars in whatever color this is, gray. So these show you the performance you can get assigning different weights to the two objectives. Okay. So they are basically doing scalarization. Okay. Alpha 1 F1 plus alpha 2 F2. And F1 is the classification loss for the top left image. F2 is the classification loss for the bottom right image. And for different choices of these weights, they got these stars. Okay. Now, if you look at only one of these images and ignore the other, you can get these yellow lines. So this is the best accuracy you can achieve if you care about only one of these images, not the other one. So if you care only about the top left image, you can get this vertical yellow line. This is the best possible accuracy. If you care only about the bottom right image, this horizontal yellow line is the best possible accuracy. Right? And these stars indicate that we are not able to simultaneously achieve the best accuracy for both of them. Right? Whatever choice of weights you can assign to these two objectives. And then they come up with a method which was based on solving this problem, which was able to achieve this intersection exactly. This green dot, this is able to achieve the optimal classification accuracy for both the images. So this hints that there is some gain to be obtained by looking at this multi-objective problem rather than just linearizing them. Okay. Any question here? Yes. So here, there are two objectives, task objective listeners. Yeah. So there are two objectives, classify complex image activity, classify bottom right image. And the objectives are like some like error function, Prof and Prof, etc. Okay. Okay. Should we take a let's take a couple of minutes break, and then any questions I'll be happy to answer, and then we'll continue.
Is that we should never be scalar the finite.
No, you will see the drawbacks later of doing this. It's incredibly hard. So that's why I said there are a lot of questions here. Basically, like things like multicast learning, meta learning, they give you significant or like varying degrees of improvement. In some cases significant, some cases not so significant. But like formally studying them turns out to be incredibly hard. Like under what conditions you would get improvement? Yeah, like in a completely new domain, in a domain you are familiar with, it's much easier to have your insights. But in a completely new domain, you don't have technical results to guide you. Are there any questions in the chat?
Sir, for example, table line, where we are just think of one task. Are we removing the other task vector or we are skipping it?
We don't care about what happens to it. So either you can take a linear combination and assign zero weight to the other, or you can just minimize. Like you are essentially just minimizing the accuracy of the problem. So the other vector is not. It's not considered, or it's assigned zero weight.
So that was collaborating because you have a small subset.
So like embedded systems have been extensively studied in a federated setting. Okay, let's continue. So hopefully I have now convinced you that whatever I'm about to do is worth doing. There is some empirical gain to be had by doing that. Okay, so like I have a few slides of math and I'll try to go very slowly. Stop me in whatever you don't understand. So what is an optimal point when you are trying to solve this problem? What do you call an optimal point when trying to solve this problem? Sorry? Minimum, right? Wherever you achieve the minimum. So now that we are trying to minimize a vector, we don't really have a unique point, as you can see in this figure. Because what do you pick? All the points, like at one point, it's one objective is better, at the other objective is better. Right. So instead of a unique point, we often get a surface. Okay. And therefore, these points are called Pareto optimal points, and the surface is called the Pareto front. Okay. So a Pareto point is where you cannot reduce one loss without making some other loss worse. Okay. So here, if you want to improve F1, you will have to go this way, and then you will make F2 worse. Okay, so all these points on this surface are Pareto optimal points. You cannot make any one of the losses better without necessarily also making the others worse, or at least one of the others worse. Okay.
By the way, this curve is generated by having a path through this space of X and plotting F2 X and F1 X. But if I had moved X in a different direction, if I reversed in a different direction in this space, I would have to use particular intersection.
Yeah.
Something like this or something.
Yeah. No, so I'm assuming that this is the best you can achieve. Yeah. You cannot intersect this anywhere. This is the best you can achieve. So under certain conditions, there's some fairly strong assumptions you can show that the Pareto is convex. So what it looks like. Okay. Okay. So then, just like in all the functions, for all the functions, we cannot minimize it all the way to the best possible minima. Similarly, now this is a harder problem. So of course, we cannot always reach a Pareto optimal point. So they come up with something called a Pareto stationary point. This is a generalization of a stationary point. So now we'll have a Pareto stationary front rather than a single point. Okay. So we will generalize gradient being 0 to the multi-objective setting. And how we generalize it is there would be some convex combination. Everyone knows what convex combination is? Who doesn't know? Please let me know. Okay, good. So convex combination, suppose you have n elements, x1 to xn. Okay. These might be scalar, these might be vectors, these might be anything. Okay, a lot of different kinds of mathematical objects. A convex combination is something like this. You take a linear combination, and these weights have to satisfy two constraints. All of them are non-negative, and they have to sum to 1. Okay, so it's a linear combination where the weights are positive, non-negative, and sum to 1. Okay. I don't think so. So concavity is usually the negative of convexity. So, but it won't make sense in this case. Yeah. So usually you have convex, like there's a lot of things in which convexity appears, but concavity usually is in the combination of functions, not negative. I have never seen a concave combination. So now what they are saying is for a point to be Pareto stationary, there should be some convex combination of the gradients which is 0. So these are all the gradients. I take some linear combination such that the weights are non-negative and sum to 1. And if one convex combination exists, which is 0 for all the gradients, that's my Pareto stationary point. Okay. When I had a single objective, then can I recover this from this Pareto stationary definition? Can I recover this gradient being 0 for a single objective? Sorry? Right, so there is a single function. So the convex combination is basically you assign weight of 1 to 1 and there's nothing else, right? So that basically reduces to this exactly when you are on a single objective. And conversely, this is a generalization of the stationary definition. Okay. Intuitively, what it means is that you don't have any direction to go in which you will be able to reduce all the objectives simultaneously. That's what a Pareto stationary point means. You cannot go in any direction which will reduce all of them. It would necessarily increase some. Okay. And just like optimality, the global minimizer of the function implies stationarity. Similarly, Pareto optimality implies Pareto stationarity. And as I said, when you are at a Pareto stationary point, you cannot simultaneously reduce all the functions. So if you are not at the Pareto stationary point, what should happen? there should be some direction which, if you go in that direction, you should be able to reduce all the functions. Okay? Yes. So in this case, because it's this kind of surface would result under very strong assumptions, so you can even achieve Pareto optimality, but usually you have Pareto stationarity only. Okay, so perhaps the simplest algorithm to achieve a Pareto stationary point is something that looks like this. You take a convex combination of all the gradients. Okay, so yeah, this is what a convex combination is. Replace these xi's with the gradients. Okay, and then try to minimize the norm of this vector. Everyone familiar with norms? Okay, good. So you're supposed to minimize this norm of convex combination of the gradients. Okay, so these rates are all supposed to sum to 1 and they are all non-negative. Okay. So MGDA or multiple gradient descent algorithm essentially solves this problem to come up in that direction. Okay, and the good thing about this algorithm is that either its minimum value is 0. What would that mean? This was the Pareto stationary point. That there exists some convex combination which is 0. So if this norm is 0, that means the vector setting inside is exactly 0. Does that make sense? Right? It's a generalization of x square. So if x square is 0, x is necessarily 0. Right? So either the minimum value is 0, in which case we are sitting at the Pareto stationary point, or what is the other possibility? No. The other possibility is you will find a direction which would reduce all the functions. Right? So whatever rates you come up with from this problem, you can use those rates, take that convex combination, and that would reduce all the objectives simultaneously. Right? That's what we looked at in the last slide. That either you are at a stationary point, and then you cannot reduce all of them simultaneously, which would correspond to this being 0. Or you are not at a particular stationary point and you can reduce all of them simultaneously. So there would exist a direction. This algorithm would give you that direction. Okay. Any questions here? Okay, so now let's look at a simple algorithm which implements this in a distributed or a federated set. Okay, this was a simple enough algorithm. You are basically supposed to solve this problem. Right? And you can solve this problem like just compute the gradient of this, and you should be able to solve this problem. Okay. And now we want to solve this problem in a distributed manner. Okay, so this is the problem we want to solve. There are n objectives, and each objective is distributed across n clients. Okay. And as you can see, each client has all the n objectives. All the n objectives. Okay, so again, recall this is what MGDA does. Okay. So if you think about the entire problem, maybe, yeah, so if you think about this problem, every machine will compute what it has, right? So what would be the, so if I want to write gradient of this in terms of gradients of these, what should I write? Tell me. Given this, what should be the gradient of this function? Gradient is a linear operation, right? So just compute the average of individual gradients. Right? So ith machine would compute its gradient, and that's all the gradients that I need. So the ith machine will compute all these local gradients, right? And then the server would just average all these gradients across objectives, just like what is happening here. Right? And then I have all these gradients. I can just simply minimize this problem. Okay. So all I need the users or the clients to do is compute these, and I'm done. Okay. By the way, how would you solve this problem if you have all these gradients? Suppose I give you gradient of LK of X. How would you solve this problem? No, that was solving this problem, but how would you solve this problem? Right, so simply do gradient descent. Now there's a constraint, so you will have to do projection, but basically projected gradient descent. Okay. Okay, so this is basically the algorithm we'll run. I'll go over it very slowly. So let me know if anything is not clear. Stop me any step of the process. So at the beginning, remember that every machine needs to compute these. And the ith machine will need to compute these for k equal to 1 to n. Okay, so this is what every machine needs to approximate. They can't compute it exactly, but this is what they want to approximate. So let's say that every machine starts from the same model. Okay, and every machine will maintain n models, one for every object. Okay, so in the beginning, suppose you download the model from the server and you start from X and you are trying to minimize m objectives. So you initialize one model for each objective. Okay. Then suppose you run certain number of updates. So for the kth objective, the ith machine runs certain number of SGD steps. Everyone knows what SGD is? SGD gradient descent. Okay. So you can run gradient descent, you can run SGD, you can run your favorite algorithm. Okay. So you are working only in this expression, you are working only to minimize the kth objective. Okay. And when you are done, you compute the difference. X is where you started from. XKI is where you reached. You compute the difference and you send it back to the server. What would this look like in this case? Suppose you only did one step of this. So instead of multiple different steps, you did one step. What would delta KI look like in that step, that case? Write it down, write it down, write it down. What would delta KI look like if you do a signal this kind of an update? Right. So what is that? It's exactly the gradient. Because you started with X, you went to XKI, you just took the gradient, multiplied it by a learning rate, and then you divide by the learning. It's exactly the gradient. This is what we want. These are what we are looking for. Right? So each user sends estimates of each gradient, one for each objective, back to the server. And at the server, for each objective, these gradient estimates are averaged. Okay. So it's this operation happening. You got these from each user, you average them for each objective across users. Okay, so for the kth objective, you average them across users. And then you solve this using projected gradient descent. And using these new set of weights, so this will give you one set of weights. And then what we discussed that either this is 0, that means you are at a station point, or it will give you a direction. So the W stars give me a direction. Okay. So essentially, every user starts with some model that the server sent. it initializes a model, one for each objective, does some local steps or does one local step, comes up with an estimate of the gradient, this gradient, for each objective. So this at machine I for each objective, or rather this quantity, sends back to the server. Server averages all these across clients, and then it simply runs the MCDS step. And now it has a direction it should go in, which should reduce all the objectives. Do you see any problem with this algorithm? Okay, let's, great point, but let's assume they are not. We are in a much simpler territory right now. Yeah, any problem you see with this? So suppose number of objectives m is 100. What would happen in this case? How much communication do we need to do? Suppose our model is 100 megabytes and we have 100 objectives. So this step, how much communication is that? This step. Right. So it's like 10 gigabytes. Every client would send 100 updates or 100 models. Right. So the problem is that we are doing, if we have m objectives, we are doing m times communication. Right. If you have 100 objectives, like this is really bad. We shouldn't be doing this. There should be a more efficient way to do this. And another subtle point is that what we did is we tried to approximate this quantity, but the way we came up with to do this is that every client for each objective runs a different model. We were supposed to learn a single model, right? So this training of multiple models, this actually leads to a very bad performance, right? Because we are not, at the clients at least, we are not learning a single model. We are learning separate models. And when we combine them, what we get is something much worse. It won't do well over multiple objectives. Okay. So I think I have 10 more minutes. I will describe the idea that we used, and then I won't go into the details of the exact algorithm because that's slightly more complicated. Okay. So the point of this algorithm, this type of MGDA, was to come up with what is the weights with which we should, what are the weights we should assign to all the gradients, right? What are the convex combination weights we should assign to all the gradients? That's what we discussed, right? That was a Pareto stationary point, where a convex combination of the gradients would give us a direction to go in, right? So this is crucial to come up with those weights. Let's suppose this is just a thought experiment. Let's suppose we know those weights beforehand. I know what the weights the server will come up with. Okay, I don't know them, but let's assume I know. Okay, and let's call those weights WKs. Now, how about this? Earlier, I was running a separate model for every objective. Now that I know my weights, I can run a single model which computes the gradients for all objectives and just take that linear combination. Right? Use those weights to compute that linear combination. If I know the weights, I don't know them, but if I know. Okay. So instead of computing training separate models, I could train a single model. And that was my problem, that I'm sending M models. If I could do this, I could send a single model because I'm training a single model. So that's the difference. Instead of training multiple models, one for each objective, I'm training a single model. And in that case, what I said, instead of sending one update for each objective, I only have a single model to send. Right? So suddenly my communication cost reduced. Now I only need to send a single model, which is what happens in single objective federated learning. So instead of sending objective-wise updates, I send a single update. This gives me it clearly gives me reduction in communication. It also addresses the other problem. Because I was training separate models for separate objectives, when I combined them, the performance was not as good. But now I'm working with a single model. And now I'll have much better performance. You can empirically verify this. What is the challenge here? What is the problem with doing this? I made the assumption that I know the weights, right? And to compute the weights, okay, so here is a slightly subtle point. To compute the weights, you need a delta case, right? These delta case for these quantities, the objective specific gradients, and these were averaged across clients, right? Now, what I'm sending is no longer objective specific. It's just one thing. I cannot distinguish between what is there for the first objective and what is there for the 10th objective. I'm sending a single thing. This requires objective specific things. That's the main challenge. Okay. And yeah, I won't go into the details of how we do that. It's a simple algebraic trick which helps us do that. Okay. So I'll send the slides. You can look at the paper, but it's a simple algebraic trick which helps us do that. And I'll go ahead. If someone is interested in theory, so one more good thing that we were able to do was that how much computation we need to do scales linearly with the number of objectives. Okay. In previous work, the computation was scaling quadratically or even worse in the number of objectives. That doesn't make sense. If I'm computing gradients for every objective, it makes sense that I will scale linearly, right? But why should I scale quadratically? So this is again, like, if you are interested in theory, so we made this improvement. Okay, so I'll talk about some experiment results in the last few minutes. So I didn't know before working on this paper that I'll be giving a talk in an NLP course. So I don't have experiments for natural language processing applications, but so Barish, the first author of this paper, actually did some experiments with something called the Shakespeare dataset, which is a natural language dataset, but they are not in these slides. So we worked with several datasets. I'll really talk about Select A, and the others are much simpler. So Select A is an image classification dataset in which there are celebrity images, and each image has 40 attributes. Okay, these are binary attributes, and they basically talk about the presence or absence of a number of attributes. So these can be, is the person in the image wearing an eyeglass, or if they have a mustache, and so on. So there are 40 such attributes, but you get a 40-dimensional binary vector for each image. Okay, and we were interested in classifying these images across all these 40 attributes. So that means we have 40 objectives, right? We have 40 objectives corresponding to each binary classification task. And this was if you look at the figure on the right, so this was the performance we got. The green curve was the state of the art, and the black and purple curves are what we were able to achieve. If you focus on the purple curve, we got almost a 10% jump in performance. This is the average accuracy across all the 40 tasks. Okay. So you might say average accuracy hides a lot of things. What if I'm doing very well on few, but horribly on the others? Okay. So this is to convince of the other case. So on the left, you see a radial plot. Okay. And we are plotting the test loss. So what is the loss value for each of those binary classification tasks? And there are 40 points on the circumference of this radial plot. Okay, corresponding to the 40 tasks. So the closer you are to the circumference, what does that mean? The larger the loss is. So these are losses, these are loss values. Okay. So the closer you are to the circumference, the worse your loss. So you want to be as close to the center as possible. Okay. So the green curve, as you can see, if you compare the green lines with the purple lines are completely inside the green area. Okay. So consistently across all 40 objectives, we were able to outperform in terms of the test loss. Okay. And coming back to the initial point, there was for a long time, there was discomfort with the fact that why we are not linearizing, why are we working with these vector objectives? So I discussed the reasons for not doing that, but in some cases, if you want to, you can linearize. And if you want to impose some preference across your multiple objectives, that I care a lot more about privacy than I care about utility. Okay. Or in recommender systems, I care a lot about relevance than I care about novelty and so on. You can impose preferences. Again, this is an open direction. Like a lot of open questions exist, but this ICML 2020 paper is a good place to start if you're interested. And finally, some of you might be interested in this. So I refer to this figure again and again. I call this the Pareto front. Now the tricky thing is that suppose you reach some point on the Pareto front, and now you change your mind and you said that I'm not interested in doing very well on F2 and not doing very well on F1. I want to give me an efficient method to go from this point to this point. If I suddenly care more about F1 than F2, can I efficiently go from this point to this point? Correct. I don't want to solve the problem again. It turns out there's no way for this. You have to solve the problem again. So this is an open question. How do we navigate from one point on the Pareto front to the other? Generalization guarantees, again, wide open. We don't understand how to get what kind of generalization guarantees we can achieve. So multi-objective optimization, multitask learning, very closely related fields. And yeah, the generalization guarantees are not understood. When would you generalize better? When won't you? Also, in a lot of applications, when you are trying to explain generalization, there are several optimization-based surrogates that people use. For example, if your optimization surface is smooth, you are expected to generalize better. Okay, you would come across this. You will come up with this across applications, computer vision, NLP, and so on. It turns out with multiple objectives, those heuristics don't work. Okay, just because you have a smooth surface doesn't mean you will necessarily generalize well. Okay, so just to summarize, almost in time, we were looking at the general mathematical problem of minimizing multiple objectives rather than a single scalar objective. And all these objectives are distributed across multiple machines. Applications contain like chatbots, recommender systems, personalized healthcare, and so on. We discussed some notions of Pareto stationarity, etc. We discussed an algorithm, the basic algorithm, which does okay, but has very bad computation cost, very bad communication cost. We were able to improve that in our paper. And yeah, we were able to improve some empirical performance. But yeah, I would strongly encourage you to explore this in your field, whatever you work on, NLP or otherwise, computer vision, etc. Robotics, there is a lot of work in reinforcement learning and robotics working with multiple objectives, because again, you have multiple objectives. You want your robot to do a task, but you don't want it to crash either. You don't want it to run out of battery either, right? So incorporating multiple objectives in robotics is again a challenging problem. So I would encourage you to, yes.
If we forget that, then the algorithm should be able to do that. Is it the core idea?
Yeah, it is the core idea, but the preferences are encoded in a very specific mathematical form. That is the limitation of it. Okay, thanks everyone. Yes, thanks.
So the symbols are a little hard for me to follow. So I have made this matrix for me. So these are the losses or gradients of this particular objective for this particular user.
Yes.
Let's say it's a n cross m matrix. What are we sending back to the server? The linear scalar of this.
So in the first algorithm, we were sending each of these. We are interested in sending some linear combination.